Swayam Prabha. Digital India. Educated India.
In the last lecture, we saw overcurrent relaying and earth fault overcurrent relaying. Today, we move on to a new type of relaying, which is namely distance relaying. Now, in distance relaying, unlike in overcurrent relaying, we use two inputs. That is, we use the input from the current transformer as well as the voltage transformer or the potential transformer. In terms of a schematic, if you were to see a distance relay, it would look something like this. If this were a transmission line, these are the two buses, and say there was a relay at this end, then it takes the input from a current transformer. This were a relay. This would, if it's just a current transformer, then it could be an overcurrent relay, or if it is getting the input from the other side, then it could be a differential relay also. But other than the current transformer, we also have a potential transformer input or a voltage transformer input like this. Okay, so this is how the schematic looks like. This of course will control the breaker, and then there is other inputs, like there is a DC input to this relay, which we have seen in the earlier classes. This is just, I'm sorry, this is not how it looks like. There's an error in this. So today we will look at distance relaying. Relaying or relays or relay. If we were to look at the schematic of a distance relay between on a transmission line between buses A and B, it would look something like this. Till now we have used relays which were the overcurrent relays, which had only a single input, that is the CT input. If this were the CT. Now we will take the input from a voltage transformer also. Okay. So it would be something like this. This is, keep in mind, this is just a schematic, right? The exact circuit connections and all are a bit different. Now, this of course has other inputs to this as well, as for example, there is a DC supply input, then the output will trip a circuit breaker. That is not shown here, only the relay in terms of the schematic is shown. Now, the distance relay is primarily used to protect transmission lines. Most of the transmission lines are protected by distance relay. Overhead transmission lines specifically are protected by distance relays. Only a very few would be protected by differential relays, but a majority of them are anyway protected by distance relays. Of course, there will be overcurrent backup and all that, but the primary means of protection for transmission lines is distance relays. So the application of distance relays are primarily in transmission line protection. Then they are also used in transformer protection in some cases, though mainly for transformer protection differential relays are used, and then also in generators for a specific type of protection, which is loss of excitation. Now the advantages of distance relays when compared to pure overcurrent relays are um, more accurate, because now it has more inputs, so more accurate as compared to um, overcurrent relays. Of course, the most accurate would be differential relays, but there is also a higher cost involved. So, um, a majority of transmission lines will still use distance relays compared to overcurrent relays. Then, since this is because it uses one more input, then this is more, this is inherently directional. To make overcurrent relays directional, you will require an additional input, which is the PT or some other current signals. But because this uses the potential transformer input as well, this is inherently directional. There are other advantages, of course, associated, that it is slightly faster in terms of computation, but the primary advantages are these two. Now we will move on to relaying algorithms. We will do the derivation of the equations on by paper and pen only. We will see a few slides, but in the next lecture. Okay, so now the model that will be using for developing these equations or deriving these equations is similar to the model, or is rather the same as the model that we use for, if you remember, for symmetrical components. So if this is the phase A, this is a three-phase transmission line, phase B, phase C, and the currents are IA, IB, and IC in the transmission line. The voltage drop across the transmission line is delta VA, delta VB, and delta VC. Okay, and the positive sequence impedance of this line is Z1. The self impedance of all the three phases is ZS, and the mutual impedances are equal. They are Zm, and so what we are assuming is, we are making a few assumptions here. One is that charging is neglected. This will lead to a simpler equation for us. Otherwise, we will have hyperbolic sines and cosines. Charging is neglected. Then the lines are fully transposed, the fully transposed transmission lines. Okay. So we will now proceed with our derivation. Now, for this line here, the voltage and current equation is given by delta VA, delta VB, delta VC in matrix form, Zn, Zs. Okay. Now, suppose on this line there were to be a fault at a per unit distance x. Okay, the type of fault we will see, but there were to be a fault at a per unit distance x. I'll just draw one phase here just for this, otherwise that diagram is a bit congested. this were, I'm just drawing phase A here, and say there was a fault at a per unit distance x. Okay. For the purposes of this derivation, we will make a further assumption that the fault impedance is zero. Okay. So say the voltage at the fault point was Vf, or in this case Va of f, then if it was a solid, if it was a single line to ground fault, then V f of A would be equal to 0, because we have made that assumption that there is no fault impedance. You can, however, make a very detailed fault model, which we are not going to do in this course, but it would look something like this. These are individual impedances, and I'm sorry, there would be switches here also. So the fault itself would be a 3x3 matrix, but we are not getting into a very detailed representation like this. We will, depending on the type of the fault, we will simplify this and make all these impedances here equal to 0. Okay. Now one statement that we will make before we start off is that irrespective of the type of the fault, what we are seeing here is the apparent impedance, or because it is V by I of that nature, since we are taking the V and I inputs. So the statement that we are making here is, irrespective of the type of the fault, the apparent impedance as seen by the relay, or ZR, will be equal to X, which is the distance at which the fault, per unit distance at which the fault occurs, into Z1, which is the positive sequence impedance of the line. Okay. Now, in effect, what we are seeing is, say there is a three-phase fault, then the apparent impedance as seen by the relay is XZ1. If there is a line-to-line fault, then the apparent impedance is still XZ1. Line to ground fault, XZ, and a single line to ground fault is also XZ. Now, you would appreciate that the right hand side here is the same. Okay, so that means we will have to configure our measurements differently here on the left hand side, so that to get the same right hand side. You can't do the same things on both sides and get a similar result. So we will see how we configure the measurements, as it is known as in the relay term, to get this quantity on the right hand side, the quantity of XZ1 on the right hand side. So we will start with firstly with the three-phase fault, or the triple line fault as it is called. Now this is a balanced fault, which means that if this is IA, IB and IC. Means that IB is equal to A square IA and IC is equal to AI, where A is equal to E raised to J, or 1 angle 1 feet. Okay. So now let's get back to our transmission line model. And what we are saying here is this. So this is the distance x, and now the voltage drop in the line is that delta VA is up to the fault point, or delta VB is up to the fault point, not for the entire line, because we are considering only the relay. The relay is located at this point, at this end here, so we are seeing only the voltage drop up to the fault point. Okay, and this VF, of course, since it is solidly grounded, we can take it as 0. So what we have, in other words, is delta VA is equal to VA minus VF. We are not qualifying as VAF and VBF and VCF because it is the same voltage, minus VBF, since delta VC is equal, sorry, VC minus VF, since VF is 0, this is VA, VB, and VC. So our transmission equations in the matrix form will become VA, VB, VC is equal to, now keep in mind that it is not for the entire length of the transmission line, but only the per unit distance x. So we take x here, Zs, Zm, Zn, Zn, Zs, Zn. Okay, so let's take the first equation. So we get VA is equal to x into Zs IA plus Zm IB plus Zm. Now, since this is a balanced fault, we have IA plus IB plus IC is equal to 0, or IB plus IC is equal to minus IA. So this equation here becomes VA is equal to x into Zs IA minus Zm IA, which is nothing but VA equal to x into Zs minus Zm. Now Zs minus Zm, as we saw in our symmetrical components classes, Z1. So VA by IA is equal to XZ1. Okay. Now similarly we can derive for the other phases also, or simply substitute in this as VB by IB is equal to A square VA by A square IA, which is nothing but XZ1. Similarly, BC by IC is equal to AVA upon AIA is also equal to X1. So now you have got three elements for a three-phase fault: VA by IA, VB by IB, and VC by IC. Okay. Before we get into the settings, we will see all the types of faults, and then get into the individual settings and what this XZ1 means and how you will set it for the line. Okay, what essentially, just we will elaborate this and extend it a bit later, but on an RX diagram it would mean something like this. This is your line angle, this is your line AB or whatever line that is, theta is your line angle, and what we are saying is if the impedance is less than the positive sequence impedance of the line, and this is your distance x here, then it means that there is a fault. We will elaborate on this towards the end of today's lecture. Now let us move on to the double line to ground. Okay, what we are saying in the double line to ground fault is this. This is, and this is the distance x in the line. Okay, you can call this also as x for the sake of completeness, and then similarly delta VA, delta VB, delta VC, and the currents IA, IB, IC. Okay. Now, in this case, what do we have? We have let's write the equation here. Now, if the voltage at this fault point here is VF, some VF, then we have 3 equations but 4 unknowns. So, it would not be possible to directly solve. So, instead what we do is we do row number 2 minus row number 3, which gives us delta VB minus delta VC, which is nothing but VB minus F minus of VC minus F, which in other words is nothing but VB minus VC. Okay. So now what does this on the right hand side imply? We will get equal to x into, let's multiply it and see. Actually the first terms will cancel, but we will just anyway write them. For the second row we will get ZMIA plus ZSIB plus ZMIC minus ZMIA plus ZMIB plus ZSIC. Okay. So this will cancel, and what we will be left with is x into ZS minus ZMIB plus Zm minus ZSIC, which can also be written as IB minus IC. Just manipulated the signs of it. IB minus IC. Okay, so this is nothing but Z1. So we have which is what we wanted. So if we were to give this input, these the line voltage divided by the difference of the line currents, then we would get XZ. Similarly, for the other two phases, we'll have VA minus VB upon IA minus IB is equal to XZ1 and VC minus VA upon IC minus IA is equal to XZ. Okay, so this will detect a B to C fault, this will detect a A to B fault, and this will detect a C to A fault. So now you require 3 elements. When we were working with the legacy electromechanical relays, then 3 elements were needed. You actually had 3 physical elements configured to read these quantities. In a numerical relay, of course, you can simply do these numerically. So you need not have 3 different elements. They can be all the same set of computational instructions in the same relay. So you don't need 3 different elements. So that saves quite a lot of a burden. Other than the fact that, of course, the relay itself has a lower burden on the CTs and PTs. Now, now what happens if there is a 3-phase fault? How do these elements see a 3-phase fault? What do these elements see rather? So let's quickly look at that. Say VB minus VC upon IB minus IC is equal to XZ1. Now assume that there is a 3-phase fault. What is VB? In case of a balanced 3-phase fault, it will be A square VA minus AVA upon A square IA minus AIA which is the same as what we derived in the earlier case. Okay, so all these 3 elements, other than seeing the respective line-to-line faults, also will detect the 3-phase faults. So we have taken care of 2 sets of faults with these 3 elements. For the single line to ground fault, however, we will have to do something different. What is that? We will see. So let's look at a single line to ground fault. Now there is an additional assumption that we make here in the single line to ground fault, is that the pre-fault load currents are 0, and say there is a fault on phase A at a distance x. So no, I'm sorry, not, this is not A. So this is a distance x, this is the phase A. Since we have assumed that the pre-fault currents are 0, it implies that IB is equal to IC. So now what do we get with the transmission line equations in this case? In this case, we have delta VA Okay. Now IB and IC are 0, so that leaves us with, and also VF is 0 here because it's a solid fault, so that leaves us with only one equation. The first equation here, we will get VA minus 0 in this case. VF, I'll write for the sake of completeness, is equal to X ZS IA plus 0. Okay. So VA is equal to X ZS IA. Now if we do VA by IA, simply do VA by IA as we did in the earlier cases, we will get X ZS, which is not what we want. Remember, we want to get X of Z1. So what do? We will now manipulate this equation here such that we get X of Z1 on the right hand side. Okay, we'll start with this equation here. VA is equal to X into, we will subtract and add ZL. Okay, now this will give us Z1, but now we are left with an extra Zn. We will have to somehow get rid of that term as well. If you remember our symmetrical component discussion, then we derived that, and Z0 is equal to Zs plus 2z. Okay. Now if I were to subtract the first equation from the second equation, these two equations, subtract the first equation from the second equation, then I'll get Z0 minus Z1 is equal to 3Zm, or Zm is equal to upon 3. Now coming back to this equation here, we will get dA is equal to x into Z1 plus Z0 minus Z1 upon 3 into I, or we further manipulate this a bit, take Z1 as common, into I. Okay. Now on the right hand side we need xz1 only, so we will get dA upon IA plus Z0 minus Z1 upon Z1, and this is IA by 3 is equal to xz. Okay, so we have got what we wanted on the right hand side. We will manipulate this part of the equation a bit. If you remember, for a single line to ground fault, we had okay, so this we will simply replace IA by 3 by I0, and since this factor here, it's just a multiplier or a scalar multiplier, Z0 by Z1 upon Z1 is a multiplier which comes along with IA by 3 we are replacing by I0. So since this is a multiplier which comes along with I0, we will call it M, or some texts also call it K, the zero sequence compensation factor. Okay, so finally the equation will look like this: dA upon IA plus NI0 is equal to xz. Now this is for fault on A to ground. For B to ground, we will need another element, which is for C to ground, one more element. So these three, along with the earlier three, which were VA minus VB upon I minus IB, VB minus VC upon IB minus IC, and VC minus VA. So these six, AB, ABC, BC, ABC, and CA, ABC. Okay, so these six elements here, 1, 2, 3, will completely cover all the faults that can occur in a transmission line. So you needed six physical elements for a distance relay if you were working with electromechanical relays. Now, of course, with numerical relays, all this can be managed in the same algorithm. You just have to configure the measurements accordingly. So how this works is, if there are 6 elements, of course, each element checks on its own. But here you can sequentially check if the xz1 or the X is less than the positive sequence impedance of the line, so that it implies that there is a fault on the line. Okay, so here you have to keep in mind that for cables, determining this M is a difficult task, because depending on where the fault occurs, the fault current may return through the sheath, through the armor, through the ground itself. And so this determination of this M or zero sequence compensation factor becomes a very difficult task. So setting of distance relays for cables is extremely difficult. Fortunately, the cable lengths are short, so important cables are protected mainly by differential protection rather than distance protection. Okay, so what will I mean, just as a sake, for the sake of interest, you can substitute, say, what will happen to what will the phase unit read if there is a say a phase to ground fault, a single line to ground fault. You can just substitute in this and see. If you work it out, you will see that it reads there will be something more other than xz1. What it means is you'll get something like VA minus VB upon I, and IB is 0 in this case, so you get something more than xz1 here, and which means that it will not pick up correctly. It could, of course, there is a chance that it could pick up if x is very low, but otherwise it will not read the fault correctly. So that is why we need more units. Okay, so we will now this covers the 6 types of units that are needed. I'm talking in terms of the legacy units. For numerical relays, these are just equations that have to be a part of your numerical relaying algorithm. Okay, or the distance relaying algorithm. There's nothing specific numerically about this. So now, how do we set the relays? Okay, now if, as we said earlier, if you were just checking, your transmission line is something like this. This transmission line angle, as we said, is closer to 90 degrees, and your xz1 will be something here. If there is a fault at this part of the line, then you just have to check, say, the z apparent by z1 is less than 1. Then your job would be done. Of course, how to set that we will come to a bit later. I mean, do you go till for the full length of the line, or you go for a little less? That we will see a bit later. But even before that, what we have done here is, we have ignored the fault resistance, if there is any. Okay, and in practical systems, you could have some impedance coming in the path of the fault. That means the fault will have some impedance, and the locus may not lie on the transmission line itself. Okay, so what we have is, this is the transmission line locus on the Rx plane, and if there is some fault impedance here, okay, suppose the fault occurred here and then there is some fault impedance, you would have to go like this. Fault occurs at the end of the line, you will have to move along the x-axis, because the R is on the x-axis. So you will have to actually check whether, instead of checking whether the impedance lies only on this line, part of the line, you will have to actually check whether it lies in this convex area here, which is a quadrilateral. Okay, so we have now added a bit of complexity in terms of the fault impedance. Now, with the legacy systems, this kind of characteristic, this is known as a characteristic. Okay, any shape of the relay characteristic on the Rx plane should be realizable by the relay itself. Okay, so now this type of characteristic was not easily realizable by in the terms of the electromechanical relay. So what was done is, what we call as the Moore relay. Okay. This is a circle which lies primarily in the first quadrant. Okay, so there are some parts which are there in the second and the fourth quadrant, but primarily it is contained in the first quadrant. So it is sort of approximating what you want, and though it is not ideal, but it serves the purpose most of the time. Okay, so this type of characteristic is known as a Moore characteristic, and this is what was used with electromechanical relays. Now, since we are not going to deal with electromechanical relays in this course, I am not going to go too much into details of settings and all that of this type of relay. But just for the sake of completeness, we'll quickly look at how it was, just one example of how it was set. Not a numerical example, but in terms of the impedances of the line and what was known as a torque angle. Okay, so now suppose theta is the line impedance angle. You had one more. This line was not the diameter of the circle. Please note that that would lie on a line which is known as a maximum torque angle line, and this the angle subtended by the line on the x-axis is known as a maximum torque angle, tau, or some other notation there. And then you had the okay, and okay, this doesn't look exactly like a circle, but it is a circle of this type. Okay, and such that the line lies completely in one half of the semicircle. Now, since this is contained within the half of the semicircle here, this angle is 90 degrees. Okay, so you can call this as Z set. Okay, now this has some history. Why torque angle and all that? Because you had the electromechanical relays, you had the voltage coil, the current coil, and a torque produced on the disc. So that is why you had this maximum torque angle. You have 30 degrees, 60 degrees, all different types of relays that are available. But we are not getting, as we said, we are not getting into that. Say if this was Z set and this was Z line, and this is 90 degrees, we have Z line. From trigonometry, we will have Z line is equal to Z set into cos of theta minus tau. Okay, and what did you set the relay at? You use Z set to set the relay is equal to Z line upon cos of theta minus tau. Okay, all these are known because the configuration of the coils, etc. Tau is known. Theta you know from your line data. Z line also you know from your line data. So you can set the. Okay, so this was by no means a complete setting of the electromechanical relay, just to give you an idea of how we went about setting the electromechanical relays. Now that brings us to the actual setting part. Okay, we will discuss this a bit because it is important, and that is how what are known as zones of distance relay are set or are defined. Okay, now assume that this is your line AB or whatever that you want to call it, and will I, okay, I'll draw the line here. Okay, now will I set this or whatever method I used for setting to cover the entire line here? If my relay is sitting here, will that Z1 or the setting that I use will that be used to cover the entire length of this line here? The answer to that question is no. And no, because if it is set to do this, then there could be other lines here. Maybe just for the sake of for this example, I'm drawing the short line here. Could be any line, could be a parallel line also. And for faults very close to this bus here, if there is a fault here, or very close on this side, or on a fault on this bus also. Okay, it becomes impossible to distinguish where the fault lies. Okay, this is for a variety of reasons. We have made certain assumptions when we started the derivation. We said charging is neglected, line charging is neglected, lines are fully transposed. This is even without the CT and PT errors. You could have a very accurate CT. You could have, nowadays you get optical CTs also. The CTs could be very, very accurate. But even without that, we have made certain assumptions which compromise the accuracy. On top of that, you have CT and PT errors. Okay. Okay. So now it becomes very difficult to sort of distinguish whether the fault is on the line AB itself, whether it is on the bus, if it is very close to the bus B. So the distinguishing of the fault, whether it is on AB, very close to B, whether it is on B itself, or whether it is on BC, close to B. So this becomes very difficult. Now, if it is on B, you would want the bus differential to operate and open the breakers of the line from this side. Also, if it is on BC, then you would want to for this side breaker to operate here. Okay, you don't want this breaker here to operate, or this relay to trip, because it will unnecessarily cause more disruptions. Okay, so to avoid this problem, we generally don't cover 100% of the line. What will happen is the more characteristic or any other characteristic, which we probably will see next time in next class, will cover only up to say 80 to 85% of the line. Okay, and that is known as zone 1 or Z1 of the relay. Now this it could become a bit confusing. Z1 we also used for positive sequence impedance of the line earlier. Now we are using it for zone 2, but that is just an unfortunate fact. We will have to get used to it. So for zone 1, or I'll write zone 1 here to avoid confusion, but later in the lectures I would sometimes use Z1 also. So zone 1 will cover 80 to 85% of the line. Okay, so primary protection now zone 1 is primary protection here, of course, because this is the primary this relay here has primary protection zone up to AB. So primary protection towards the for the last 15 to 20% of the line. 90% also you could go up to, but generally it is in this range only, 80 to 85% of the line is deliberately, smoothed down. Okay. Because you want the other protections to operate first. Okay, so I hope this is clear. What you do is you don't let the zone 1, or you don't set the zone 1 rather for the entire, to cover the entire line. And I'll just draw it by a dotted circle. If it was covering the entire line, it would have been this. But you cover a 10 to 15% less. Okay, I will remove that because it's not used in any case. Correct this figure. So now, what happens to the 10 to 15% of the line which is not protected as yet? We can't leave it unprotected. Okay? We can slow down the protection, primary protection, but we can't leave it unprotected. There are other relays on the other side and all that, but from the point of view of this relay here, it is still in its primary zone, so we can't leave it unprotected. So what do? We define another zone of protection, which is zone 2. Because this is zone 1, we define another zone of protection. And how long does it extend? It can extend up to B, but just to be sure that since we are extending it in any way, we also extend it a bit beyond B. How much beyond? So about 20% more. So about 1.2 times of AB. So this can be, this is a zone, which is 1.2 times the length of AB. Later in the next class, we will see how generally this is extended even further. But for now, for today's discussion, we will keep it at 1.2 times. And when we say slowed down, how much slow? So this is usually slowed down by a interval which we have seen earlier, the coordination timing interval, which is 250 to 300 milliseconds. So zone 2 time is slowed down by 1 CPI. Okay. So now this part of the line. Okay, I'll draw it again. So up to say 80 to 85% is zone 1, and then beyond that 20% more will be zone 2. Okay, and this timing is slower by about 300 milliseconds. This there is no intentional time or intentional time delay for zone 1. Okay, it's an instantaneous. So what will you will have the 6 elements that we saw will be there for zone 1, and then will be there for zone 2 as well. So what it usually does is checks whether it is in zone 2. Then if it is in zone 2, then also it will further it will check whether it is in zone 1 as well. If it is in zone 2, then it can wait for up to 300 milliseconds. If it is in zone 1, the trip has to be instantaneous. This is in terms of the electromechanical relays. What happens with numerical relays is your code it's just a part of a single algorithm. So it will first check, you will have these 6 checks for phase faults, and then earth fault. The six equations that we described earlier, and it is continuously checking. And if it is both for zone 1 and zone 2, so first it will check for zone 2, and then it will check for whether it is the if it is not in zone 1, whether it is if it is in zone 1, it will check further. If it is in zone if it is in zone 2, it will further check if it is in zone 1 as well. Okay, and if it is in zone 1, then there is a trip is instantaneous. If it is in zone 2 but not in zone 1, then the timer can run out up to 300 milliseconds. Now we have covered up to say 20% of this line. Okay. Now this relay here can also, or rather should also, provide a backup to this relay here, which is covering this line here. Okay. So to cover the rest of the line, we provide another zone, which is zone 2. Okay. Now which looks like this here. We have another zone, another circle with a larger radius here. Now because it is covering the line BC here, you have to give a chance to the primary protection of that line to clear the fault, and also slow it down further from zone 2 also. So the minimum is about 2 CTI or 600 milliseconds, but usually zone 3 timers are set to about 1 second, and some references like third zone revisited by Professor Swarke and Horowitz have also mentioned that the delay can be as long as 90 cycles, which is 1.8 seconds for a 50 Hertz system. Okay, so now in our algorithm, in addition to Z1, Z2, there will be a Z3 also. So first the algo will check for Z3, then it goes and checks for Z2 and Z1. Here it waits up to whatever time that you have set, say 1 second, here 300 milliseconds, and here there is 0, so that is instantaneous. Okay, so first it checks for Z3, then it checks for Z2, and then it checks for Z1. If it is in Z3 but not in Z2 and Z1, it waits for 1 second. If it is in Z3 and Z2 but not in Z1, then it checks for 300 milliseconds. If it finally falls in Z1, then there is no wait at all, it will trip in instantaneously. So we will stop here and look at more details of settings and other aspects of distance reading the next time. Thank you.